morning. So now we start the record of the next chapter, which is chapter number 9. And the title is Maxwell's equation. So let me quickly take you to what are the topics that you will be studying here, or basically the concepts that we are going to cover. So the first is going to be the induced EMF arising from Faraday's law. The second is going to be the concept of the displacement current, which we left in the previous chapters. Thirdly, we look at Maxwell's equations, the 4 equations, how they look when we apply dynamic fields. Till now, what we have seen is only static. Then moving from there, we would be talking of Maxwell's equations in terms of scalar and vector potentials. And finally, we would also be writing Maxwell's equation in the phasor form. The reason why we need to do that is in certain chapters, it becomes elegant. The mathematics will be elegant only when you go for the phasor form. Okay, with this introduction, I would like to get on to the chapter. So once more, in a line, if I have to look at what is the objective of this particular chapter, it's going to be setting up the 4 equations and then use the 4 equations, play with the 4 equations, and then try to find out the unknown parameter. Like for example, the electric field is given, you don't know the magnetic field. Or there is a parameter called beta. Beta is the phase of the wave, okay, or omega, the angular frequency. Okay, so there could be always a situation where you have 1 or 2 inputs given and the others have to be evaluated using Maxwell's equation. That's going to be the crux of it when it comes to numericals. Now let's start off with what we have studied. We talked about static or time invariant fields. So what's the meaning of static time invariant fields? So if you look at how the electric field is written, you will always find that electric field is going to be a function of x, y, z, meaning only position. Okay, and what would be the source of this kind of a field? It's going to be stationary charges. Okay, then let's go to magnetic field in statics, or we'll talk about magnetostatics. So there it's a steady current, which would be obviously DC current having the same value. Okay, that would be the source of a magnetic field in static condition. Or you could be talking about the poles of a magnet. Around the poles of a magnet, you have magnetic field, which is again a static field, provided the magnet is kept stationary. And another thing about these fields is that electric and magnetic fields are always independent of each other. The value of the electric and the magnetic fields will be independent of each other as long as you are talking of static situation. Okay, now let's move to electrodynamics. When you move to electrodynamics, obviously you can see here that a magnetic field that will be produced is going to be produced because of currents which are changing. Okay, time varying currents. Time varying currents can produce electrodynamics. Okay, or let's talk about accelerating charges can produce time dependent fields. I'll give you an example. When you're talking about your antenna, the oscillating electrons in your antenna can give rise to radiation or the signal. Okay, and another big difference between static and electrodynamics is quite obviously the equations involving electric field and magnetic field would be functions of position and time, unlike in static fields. Then the last important thing that I must tell you here is that in electrodynamics, electric field and magnetic field are not going to be independent of each other. There will be a definite relationship between them. Okay, you cannot randomly have an electric and magnetic field value because they are interdependent on each other. That you're going to see in this particular chapter. The best example I would give you is going to be your electromagnetic waves itself. Okay, electromagnetic wave is a transverse wave. It has got an electric field, it's got a magnetic field, both mutually perpendicular to each other and to the direction of propagation. And you will see that these two equations representing the electric field and the magnetic field have a finite relationship. And how this relationship is going to be for the different types of media, like for example, free space, or let's talk about conductors, or you're talking about the other kinds of dielectrics. In each of these, we'll have to set up equations and find the relationship between electric and magnetic field. Okay. Now from here, let's go to the next slide. Okay, so we talked of electric field. Now, what are the sources of electric field? Until now, you know that fields can be produced by charges. So when I'm saying charges here, it is assumed that the charges are not moving, they're static charges. So in this situation, the field that you're getting, the electric field that you're getting is a static electric field. And if you draw the field lines, okay, the field lines will originate from a positive charge and then end on a negative charge. And you've also seen in the previous chapters that this electric field is a conservative field, meaning the work done for a closed path equal to 0. Now let's come to, that conservative nature of the field is what is your Maxwell's second law or second equation. Let's go to another source for electric field. The second source for electric field is going to be EMF. Okay, electromotive force can also give rise to electric field, and the electric fields that are created by EMFs are not going to start on a charge and end on a charge. They will form closed loops. They will form closed loops like your magnetic fields. And straight away you can see that these fields created from EMF are not going to be conservative. Okay, because I told you they are going to be like your magnetic fields. Now, when I said EMF source, what can be the EMF sources that you come across? It could be a battery, it could be an electric generator, it could be a cell. When I'm talking of cell, it can be a fuel cell or a photovoltaic cell, etc. And what is the job of these EMF sources? The job of the EMF source is to convert energy from one form to the other. Okay, like for example, it could be chemical energy converted to electrical energy. So this is the job of your EMF source. So to quickly see more about it, I have shown you a circuit here. Okay, there is a circuit. There is a battery. The EMF source in this case is a battery, and the rest of the circuit comprises of a resistor R. Okay, so now let's see the fields. Certainly there is going to be a current. The direction of the current I is given to you. Okay, and what else is marked here? You can see in red color positive symbols marked there, which indicates that one of the, here I will not say plate because it's not a capacitor, so we should talk about the terminal. One of the terminals of the battery is positive and the other is negative, which means one of the terminal is at a higher potential when compared to the other potential or other terminal. Or I can say that there is a potential difference between the two terminals of your battery. Okay, and as a consequence, let's see what the fields are going to be. If you look at the current direction is clockwise as seen on my slide. Okay, and that is obvious because the current will flow from a higher potential to a lower potential. Okay, and also there are some fields marked there. You can see a field EE marked there. What is field EE? The field EE is the electrostatic field. The electrostatic field EE, which is equal to minus del V, what we have studied in the past. Okay, so that field is certainly from the positive to the direction of the field will be from positive to the negative. Now, between the plates or between the terminals of your battery also, okay, from positive to negative. Therefore, you will see that the field EE is in the opposite direction inside your battery as compared to outside. Okay. Then additionally, there is also another field that is given there for you. that field is your EF. There is another field given there that is called your EF, and this field is the field produced by the EMF. This is the electric field that is produced by EMF. Okay. Now let us see what would be the effect of each of these fields on your current. Okay. So for that, you can quite simply see that the net field E is going to be the sum of the field produced by EMF plus the electrostatic field. Okay. And as I just said, this field produced by the EMF is 0 outside the battery. It is only between the terminals of the battery. Okay. But then EE is there both outside and within the battery, but they are in opposite directions in both these places. Okay, now what we want to do is, let us try to integrate E over the complete circuit. Let's try to integrate E over the complete. It's a loop. Okay, you're going to do the integration over the loop. So you can split it into two parts, write it as a sum of two integrals. One is going to be integral of EF dot dl and the other is going to be EE dot dl. Okay. Now you can see that the second part, integral EE dot dl, has to be 0 for the closed loop. Why should it be 0? It has to be 0 because of Maxwell's second equation. Because of the conservative nature of this field, for a closed loop, the integral will be 0. Okay, now let's come to the other part. When you come to the other part, you can write integral E dot dl is going to be integral EF dot dl through the battery. Why only through the battery? Only through the battery because you can see that, okay, you can, let me just draw a picture for you. You can see here that, you know, one of the terminals was positive, right? The other was negative. And what was our direction of EF? The direction of EF was this, right? This was the direction of EF. It was from the negative to positive. The direction of the field was from negative to positive. Okay, so that's the difference between your electrostatic field and this particular field. Okay, that's why it is called EMF. That's why it's called EMF. It is a force that is going to push your charges against what normally happens. Normally, you know that current will flow from high potential to low potential. That naturally happens. But here what is happening? Between the terminals of the battery, you're pushing current from the negative, from a lower potential to a higher potential. To push current from a lower potential to higher potential, you know that an external agent has to do work. The battery is that external agent. Okay, so what is the work it is doing? It is converting chemical energy into electric energy. So it's pushing. Okay, so your integral therefore is going to be from N to P. Is that clear to you? Okay, so now the value of integral E dot dl is going to be integral EF dot dl through the battery, and it is this integral EF dot dl which is called your VEMF. This potential difference was created because of this particular field. Okay, so VEMF is equal to integral EF dot dl, and that is simply your integral E dot dl. Okay, because the rest of it, your electrostatic force, for a round trip, it was giving you a 0 value. Okay, therefore integral E dot dl is going to be equal to your I into R. Okay, that just comes out from your Ohm's law. Okay, so from this, what do you conclude? You can conclude that electrostatic fields cannot push currents continuously through a closed circuit. It cannot maintain a steady current in a closed circuit. Why? Because it's a conservative field and integral E dot dl is equal to 0. It cannot do non-zero work. So then what is actually creating the steady current? The steady current is created because of the EMF provided by your battery, or it is because of the field created by the EMF. So that's the first thing you are learning in this particular chapter. Okay. Now let's move to the next slide. Okay. So with this background, let's move to Faraday's law. Okay. So what does Faraday's law say? Faraday's law says that the induced EMF, Faraday's law says that the induced EMF in any closed circuit is equal to the time rate of change of the magnetic linkage by the circuit. Let's try to look at the equation of it. So what's the equation? V EMF is equal to minus d lambda by dt, okay, which is equal to minus n d phi by dt. Let's see what these terms are. What is n? N is the number of turns in the coil, okay, and what is phi? Phi is going to be the magnetic flux. You know the expression for magnetic flux. Magnetic flux is integral B dot ds. Okay, so that's your magnetic flux. So you're talking about an area integral. So which area are you talking about? You're talking about, let's say you have your circuit. Okay, this is your loop circuit. So which is the area you're talking about? You're talking about the area enclosed by this particular loop. When I'm talking of area enclosed by the loop, please don't think that the area has to be a flat area. It can even be a curved area. It can even be a curved area. Okay, but basically an area with the rim as your circuit. Okay, so that's your flux. Next, what is lambda? Lambda is equal to n into phi. What is n? N is the number of turns. Lambda is equal to n into phi, and this n into phi is called the magnetic flux linkage. Okay, and then additionally, you are also seeing a minus sign in equation 2. Okay, you're seeing a minus sign in equation 2. This minus sign comes from Lenz's law. And what does Lenz's law say? The Lenz's law simply says that, okay, the induced EMF should oppose the change in flux. The induced EMF should oppose the change in flux that was responsible for this induced EMF. Okay, maybe I'll just explain this using a small example. Okay, let's say I have my circuit here. It doesn't have any EMF source, no battery. Okay, so you should not be seeing any voltage, you should not be seeing any current, right? So now what you do is, let us apply magnetic field. Let us apply magnetic field. Okay, and let this magnetic field change as a function of time. If this magnetic field is increasing as a function of time. Okay, now what do you do? If this magnetic field is increasing as a function of time, okay, if d of t is increasing as a function of time, that would imply that flux is also increasing as a function of time, right? If flux is increasing as a function of time, that means d phi by dt, that means d phi by dt is positive. Flux is increasing. So what should your circuit do? Your circuit, okay, should create an EMF. It should create an induced EMF and a current to oppose this. What is the meaning of opposing this? I want you to remember your right hand rule. If I have a current, use your right hand. If I have a current as indicated by my fingers, this current will create a magnetic field or flux in the upward direction. Okay, so look at my figure again, look at my loop. So if there is an induced current like this, then it will create a magnetic field in the upward direction. So what will happen to the initial magnetic field? The initial magnetic field and your induced magnetic field will add up, right? That is not what will happen. Lenz's law says that if the magnetic flux is increasing in this direction, then your circuit has to create a magnetic field or flux in the opposite direction to counter that increase. Okay, so now use your right hand rule. using your right hand rule, you will find that you need to create an EMF. The induced EMF or induced current will be like this. Okay. So according to my figure, let's go back to my figure. Okay, if I go to my figure, the current will be like this. My induced current and EMF will be like this, so that they can produce their own, okay, so that it will produce its induced flux or induced magnetic field in the opposite direction to counter that increase. So that's what your Lenz's law says. Okay, on the other hand, just think about what if, okay, the magnetic field and the flux are like this. So it is, magnetic field is decreasing with time. If it is decreasing with time, what should your circuit do? Your circuit should create an EMF, an induced EMF and current to help and create a magnetic field in the same direction. That's what is Lenz's law. Basically, it should oppose the change. Okay, now let's go ahead. Go to the next slide. Okay, now when we are talking of EMF, there are two types of EMF that we need to discuss. Two types of induced EMF that we'll be discussing. The first is called the transformer EMF. Okay, and the second is motional EMF. Let us see what they are. So what we are doing now is we'll go back to the Lenz's law equation, or let's go to the Faraday's equation. And how did we write that equation? V EMF is equal to minus N into d phi by dt, right? This is what we wrote. Okay, so now let's put n equal to 1 in this equation. When we put n is equal to 1 in this equation, you are going to get this. V EMF is equal to minus d phi by dt. Okay. And what is flux? You know flux is equal to integral B dot ds. Okay. Which will be equal to B into S if B is uniform. If B is uniform. Otherwise, you only have to consider integral B dot ds. Okay? Okay, so that's your equation now. Okay. Now what we do is, just a few minutes back, we have seen that VEMF, the EMF voltage, is integral E dot dl. Right? That's what we have seen. Now, please, I want you to remember one thing. When we studied physics, you remember we wrote V as minus integral E dot dl. Why did we write minus? Because that electric field was a static electric field. And here we have seen that, you know, this EMF electric field is in the direction opposite to that. So that's the reason that minus sign is not there. Some of you, not everybody, I know most of you are not going to bother, but at least one of you will remember that P is equal to minus C dl is what we studied. What happens to the minus? That minus is not there because we are talking about a different field. Now we are talking about a dynamic condition. Okay. So now let's look at it. VEMF is equal to integral E dot dl. Okay. So instead of VEMF, let's put integral E dot dl. Remember, this is a line integral, whereas on the right hand side you have a surface integral. Okay. So this is going to be, equation 3 is going to be the new form of your Faraday's law. Okay, and what is interesting about this particular equation is that this shows you for the first time that electric field and magnetic field are related to each other in a dynamic situation. What was dynamic here? You know, where did dynamic come from? What was dynamic here? What was dynamic? Your magnetic field. Your magnetic flux kept changing. Your magnetic field was changing as a function of time. Therefore, flux changed. Because of that, an electric field has been created. Okay? Therefore, you're seeing that one is a consequence of the other. Okay? One is a consequence of the variation in the other. Or for the first time, we are seeing that electric field and magnetic field are related to each other. They are dependent on each other. They are no longer independent like in the case of statistics. They can coexist and be related to each other. Okay. Now let's go ahead. Come back again to Faraday's law in this form. Now what we do is, we said changing magnetic flux. So what is the condition for induced EMF to be there? The condition for EMF to be there is going to be changing magnetic flux. Right. Now, how do you change magnetic flux? How do you change magnetic flux? For that, I want you to look at the expression for the magnetic flux. This is the expression for magnetic flux. Okay. Now, how do you change it? Okay. One way of doing that is going to be, keep your loop stationary. Okay. Keep your S a constant. Don't change that. Don't move it. Okay. Change your B. Change your B. So when you do that, what will happen? Change your B. So what happens? So you are going to now talk about dou by dou t of phi is going to be dou by dou t of integral B dot ds, okay, which will apply to B, or integral dou B by dou t dot ds. Okay, so that's what will come from condition 1. So what should you do? Keep your loop stationary, change only the magnetic field. Okay, now what's the next way? The next way of doing the change in magnetic flux. Okay, how do you achieve the change in magnetic flux? So the next way of doing that would be having a loop. Okay, having a loop, the area of which is going to change. Having a loop, the area of which is going to change, or area is a function of time. When area becomes a function of time, what will happen? Your dou phi by dou t in this case is going to be equal to integral B, okay, B dot ds, all right, but you're going to apply this, okay, you're going to apply this not to B, you're going to apply this to your area. Is that clear? Keeping your B a constant. Now, what is the third way of doing it? Here, the third is a combination of A and B. Third is going to be a combination of A and B. So what do you do here? You have a loop, the area of which is changing, and at the same time, you have a magnetic field, which is also changing. Okay, so now when you do a time differentiation, you're going to get two terms. You will get two terms. One, keeping your area constant and then differentiating magnetic field. The second is going to be keeping the field constant and considering field as a constant and doing the differentiation for the area. Nothing. I'm just saying that you have to now think of it as something like d by dt of, let us say, A dot B. So what do you do here? You will get two terms. First is going to be dA by dt dot B plus A dot dB by dt. Is that fine? Or you're going to get two terms when both become time dependent. Is that clear? Okay. So now let's go ahead and see how to deal with each of these. Okay, so here you have a circuit. You have a circuit here. Okay, this loop has a resistor. Okay, and otherwise there's no other EMF source. And I have indicated for you a current I as a function of time. A current capital I as a function of time. And you know that a current creates a magnetic field. This you have studied previously. Okay, in magnetostatics also we have seen that a source of current, a current can create a magnetic field. And if the current is a loop, then the magnetic field that it creates is going to be given by the right hand rule. Okay, so let's say that there is a magnetic field produced, and this magnetic field that you're getting is a function of time because current is a function of time, and you know that the magnetic field is going to be proportional to the current. Fine. Now what we do is, let us understand what the flux is going to be. Because B is a function of time, okay? Why is B a function of time? B is a function of time because I is a function of time. Because B is a function of time, then you're going to get flux is also a function of time. Flux is also going to be a function of time. So if flux is changing as a function of time, then you know that there is going to be an EMF. Okay, so let's look at this figure for example. Here it says that the field B is increasing as a function of time. Why is it increasing? It is increasing because the current is also increasing as a function of time. So flux is increasing as a function of time. So then what did I say? There should be the induced EMF and induced current. It should no longer be in this direction. It should be in the opposite direction. Applied current is in this direction and it is increasing. Therefore, induced current should be in the opposite direction. Okay. So this kind of a situation is called transformer effect. So what really created the induced EMF? The induced EMF and induced current have been created because of a transformation in the primarily applied current. You have primarily applied a current, okay, and then you varied that current, thereby creating a varying magnetic field and flux, and because of this variation you have created an induced EMF or an induced current. That's the reason why this is called a transformer effect. This kind of an EMF is called a transformer EMF. Now let's look at the equation for this. Okay, so V EMF in this case is going to be integral E dot dl, and that's going to be equal to minus dou B by dou T dot ds. Why this dou by dou T is only coming to B? Because as I wrote in the previous slide, only B is a function of time. Okay, flux is a function of time. Within flux, B is a function of time. So you're going to do partial differentiation with respect to time. Is it fine? Okay. And let's also, for the sake of completion, look at this E. What is this E? This E is the field due to the applied current. And what will be the induced EMF? The induced EMF is going to result in an induced current in the opposite direction. So this is what is your induced current resulting from the induced EMF. Okay. So what have we done here? We have kept the loop stationary and we only varied the magnetic field. How did we change the magnetic field? By changing the primarily applied current, by changing the applied current. So the time varying current produced a time varying magnetic field, which in turn produced your EMF. Okay, next, how do you complete this? To complete this, what we need to now do is, let us apply Stokes theorem. Let us apply Stokes theorem. The minute you see a line integral, think of Stokes theorem. Okay, and let's apply Stokes theorem. Integral E dot dl, you know, is del cross E dot ds. Now apply that and then look at the right hand side. So quite simply, you're going to see that del cross E equal to minus dou B by dou T. So this is going to be your Maxwell's equation for a time varying field. I'm not saying flux. I'm saying this is Maxwell's equation for a time varying field. Okay, and this effect is called the transformer effect. Okay, and what is the interpretation of this equation? Let's go back and look at the equation. Del cross E is not equal to 0. Why is it not equal to 0? Because magnetic field is changing as a function of time. That's why all this discussion. Therefore, the right hand side is non-zero. Whenever curl of a vector is not equal to 0, what do you conclude? What do you conclude? You've seen this in the past also. Del cross magnetic field was equal to J vector. Del cross H was equal to J. Similarly, here you are getting del cross E equal to minus dou B by dou T, which is non-zero. So just as we discussed there, here also we will say that the electric field produced because of EMF is non-conservative. Okay, so just like there, we got the magnetic field is always forming a closed loop. This electric field also will form a closed loop. It doesn't start on a charge and end on another charge. Okay. Next, let's go to the next type of EMF. The next type of EMF is called motional EMF. So see what is written here. You are going to move a loop or a part of a loop in a static magnetic field. Here, B is going to be a constant. B is not a function of time. Now to discuss this, I will have to just remind you of something. Let us say that you are talking about a charge. Let's say you're talking about a charge, positive charge, okay, which is in a magnetic field, a charge in a magnetic field. Then your motional field, I hope you remember, the magnetic force on it is going to be equal to Q U cross B, where U is the velocity. Q U cross B, Q is the charge. Now, if I bring Q to the denominator here, okay, so what is it going to give me? Force per unit charge is going to give you your field, right? And I will use this suffix M just to say that this is a field that is created. This is an electric field that is created because of the motion of the charge. Because the charge moved in a magnetic field, there is a force. And this force per unit charge is going to be the electric field. So this electric field that has been created is called the motional electric field. So that's how you're getting this equation, EM equal to U cross B. The equation comes because of that. Okay. Now, so what did we do here? How should you do this? I mean, how do you use this concept in your loop? So in your loop, what you can do is move your loop, okay, out or into a region of magnetic field. You have a fixed region of magnetic field. Let us say I have a fixed region of magnetic field, and then I move my loop, a complete loop, in and out of the magnetic field. You're going to change the flux. So this is motional EMF. Or what you can do is you can take your loop. The loop itself is there. Okay, let's say you're going to talk about a loop. This is your loop, and there is a uniform magnetic field. Let's say this is my uniform magnetic field. Okay, this magnetic field is a constant. It's not changing as a function of time. So what we can do here is move a part of the loop. Move a part of the loop. When you move a part of the loop, that moving part, okay, is going to have a motional EMF, okay, or there is going to be an induced EMF produced, okay, and this induced EMF, which is happening on the moving part, is going to drive a current through the rest of the circuit, an induced current through the rest of the circuit. So this is called motional EMF. So this is called motional EMF because here primarily the EMF is produced because of either the entire loop moving in and out of a magnetic field region, or because a part of the loop was moving. So it's got something to do with the motion. Is that fine? And how do you write the equation here? You have seen that VEMF is equal to integral E dot dl. In this case, E is EM. Substitute for E, so that's going to be U cross B dot dl. And one thing that you will notice is that there is no minus sign coming here. You will not see a minus sign written there, because when I do a problem, you will understand there is no need of putting a minus sign here, because in the integral itself, okay, the sense of integral that you will realize when I'm working out a problem, you will see that Lenz's law gets incorporated. Lenz's law will get incorporated when we are doing the problem. I'll show you how Lenz's law gets incorporated inside this integral. So in the integration itself, the way the integration is going to be defined itself, Lenz's law gets incorporated. So there's no need of putting a separate minus sign. Okay. Okay. And there is also another name for motional EMF. Motional EMF can also be called flux cutting EMF. Okay. Why did the name flux cutting come? Let us just go to your figure below. There's a figure here. I think I've gone to the wrong slide. Okay, let's go to the figure below. When you go to the figure below, so what is the figure? You have a DC machine. Okay, so what do you have here? You have the poles of the magnet. So there is a magnetic field. Okay, and then you have your loop. And what do you do with this loop? This loop is going to be turned in the magnetic field. When you are turning the loop in the magnetic field, you are changing the angle between the area vector. The plane of the perpendicular to the plane of the loop is your area vector. You are going to continuously keep changing the orientation of the plane with respect to the magnetic field, or you're going to change in the equation. In the equation, flux equal to, what is that? Okay, in the equation, flux is equal to integral B dot ds. Here, I assume that B is a constant, so I can simply say that this is going to be B dot S. Okay, if B is uniform. Now, if you see what is going to actually happen here, the area of the loop is not changing, neither is B changing. Both these are not changing, but what will be changing is the angle between them. So B dot S is going to be equal to B S cos phi. Phi is going to be the angle between the B vector and S vector. So here, when you're going to do a differentiation with respect to time, when you do a differentiation with respect to time for B dot S, it's going to be BS cos phi. So you will be doing the differentiation for this phi because phi is going to be a function of time. D and S will both be constants. Okay, so this also comes under motional EMF. This also comes under motional EMF because the loop is turning in a magnetic field, and when it is turning in a magnetic field, it's basically cutting the flux each time it is turning. That's why it's also called the flux cutting EMF. So here is an example given to you, and we'll have to set up the equation also for this. Okay, so let's see what we have in our figure. We have a part of the loop moving. So I have two railings. I have two railings with a resistor. The railings are also conducting materials. Okay, there is a resistor connecting them, and then there is a metallic rod. Okay, and this rod is moving. This rod is able to move. It's able to move without, let's assume, let's forget complications like friction and all that. It is able to slide on these two rails. We call them rails because this rod is going to slide on it. Okay, so what will happen? There is no source of EMF here. Okay, and you're seeing that there is an XY axis, and then you can clearly see here that let me use my right hand rule, X to Y. Therefore, the Z axis is towards me. The Z axis is towards me. So the magnetic field is in the minus Z direction in this particular figure. It is into the plane of the board. Okay, and you can see that this rod is going to, this conducting rod is going to move with a velocity u. So when it is moving with a velocity u, what is going to happen to the area inside? The area inside is going to increase. When the area is increasing, okay, S is going to increase. When S is going to increase, what is going to happen? Flux is going to increase. Flux is going to increase means there has to be an induced EMF in the opposite direction to counter that increase. Okay, but only thing here is we are going to explain this in terms of motional EMF. So let's read what is given here. When the rod moves between the pairs of the rails, there is a change in flux. There is an induced EMF and current that is appearing in the loop to oppose this change. Okay, let us try to understand the equations for this. What will be, you know that when you put a current carrying conductor, or you take a conductor, okay, and move it in a magnetic field. Okay, there will be motion of the charges. There is going to be a current. Okay, and what is going to happen to this current carrying conductor? Or before going there, let me just talk about, there is initially no current. The area increased, flux increased. Okay, so your loop has to create a current and a magnetic field opposing this applied magnetic field. Opposing this magnetic field. So how will it oppose this magnetic field? It will oppose this magnetic field by setting up an induced current like this. By setting up an induced current like this, and look at my thumb now. The thumb shows the induced resultant magnetic field, which is in a direction opposite to the applied B. Okay? Okay, so that's the reason why the rod is having a current in this direction. Now, what happens to a current carrying conductor in an external magnetic field? A current carrying, that was the beginning of the last chapter. Okay, what happens? It will experience a force. What will be the force it experiences? Okay, what will be the force it will experience? It will experience a force F M equal to I, if I is the current, I L cross B. You have seen this, right? But now you're seeing that the vectors are perpendicular to each other. What is the direction of L vector? L vector will have the same direction as I. Okay, you can see from the figure that L cross B. Okay, L and B are going to be mutually perpendicular. Okay, use your right hand rule for the cross product and look at the direction of Fm. Okay, I cross B, L cross B. So shows force. Okay, so that's what is the magnetic force direction given here for you. Okay, the magnetic force direction here is given. Here is given this way. Okay, so there is a force in this direction. But what is happening to the rod? The rod is moving in the opposite direction. And because the rod was moving with a velocity in this direction, there is a current. And what is this current and the magnetic field trying to do? It is trying to create a force on the rod, trying to oppose that increasing flux. Okay, now let us set up the equation. So what is going to be VEM? VMF is going to be integral EM dot DL. EM, you already got the expression, that is U cross B. So U cross B dot DL equal to UBL. Why UBL? Because all of them are mutually perpendicular to each other. Okay. Now come here. We are going to apply Stokes theorem here. Okay, I told you, whenever you see a line integral, try to see if there is a Stokes theorem possibility. So integral EM dot DL equal to integral del cross EM dot DS. No, substitute del cross U cross B dot DS. Or from here, you're going to get the expression for del cross EM. Del cross EM is equal to del cross U cross B. Del cross U cross B. So this is your differential equation. Okay, now this is what I was trying to tell you a few minutes. When you do a problem, you will understand, I told you, remember? So when you do this integration of EM dot DL, okay, on the rod, okay, please remember, when you do the integration, you have to do your integration only for the rod, only for the moving rod, between the ends of the moving rod. Why only between the ends of the moving rod? You have to do it between the ends of the moving rod because the motional EMF is there only for the rod. But because it's a closed loop, it is going to create a current in the loop. But the motional EMF is only going to be for this part of the moving circuit. The moving part of the circuit is only your rod. And when you do this integration, though it's a closed integration, but you will do within the limits between the two ends of the rod. So now, will you do it from, let us say I call this as A and I call this as B. Will you do from A to B or B to A when you do the integration? How do you fix the limits? So there what you have to do is, you have to do the integration in a direction opposite. You have to do the integration opposite to the direction of u cross b. What is the direction of u cross b? U cross b direction is the direction of current. I'll take you back to the original figure. So here u cross b. U cross b, if you do, it is giving current in the upward direction. U cross b will be the direction of the motion of positive charge, and that is going to be the direction of current. So in this figure, for example, you are going to see that the current is from down to up. Therefore, your integration will have to be from top to bottom. Okay, so it is this limits of integration which is going to take into account your Lenz's law. That's taking care of your Lenz's law, so you don't have to put a minus sign. Okay, these things will now feel like Latin and Greek only. When we do problems, it will be clearer for you. Next, let us go to the third situation. So what is the first one? Situation A was transformer EMF. Situation B is motional EMF. So the third is going to be combination of both. In transformer EMF, what happened? Magnetic field was changing. Area was a constant. In the second situation, what was happening? B was a constant, but the loop was part of the loop moved, and therefore the area was a function of time. That was motional EMF. A part of the circuit moved. Now the third possibility is moving loop in a varying field. So both. So how do you get that? So now what you need to do is your EMF, induced EMF, is going to have contribution from both of them. So just add them up. Just add up both. Okay, therefore, add up equation 7 and 8. The right hand side of add up means don't write 2 times VEMF. Okay, so adding up means just taking both these effects into consideration. This part, the first part of right hand side is going to be from transformer effect, and the second part is going to be from your motional EMF. Okay, and you can actually look at this, and when you're talking, you applying Stokes theorem, which we already did in parts there. So when we add up, you get del cross E equal to minus dou B by dou T plus del cross U cross B. This is your differential form, and what you have above equation 10 is your integral form, and this equation is called modified Faraday's law. Modified Faraday's law. So the effect of moving from a static situation. In static situation also we wrote Faraday's law. So what did we write there? We wrote VEMF is equal to dou phi by dou T. Okay. Now we have modified Faraday's law, and we are getting a modified equation. Or in other words, we have taken into effect the variation of the flux, which can be because of two reasons. One could be because of the field itself changing, or the other is a motion in the loop. Okay, so that's the reason why this is called modified Faraday's law, and this equation will show you that a change in a magnetic field can create an electric field. So they are no longer independent of each other, they are dependent on each other. So what I will do now is I'll stop the recording, and the next recording is going to be on the problems. We will see 3 problems. I will record the 3 problems. The first problem is going to be transformer, the next is going to be motional, and the third is going to be a combination of both. Okay, with that, you should be able to sufficiently understand the concepts. Good day.